Hello everyone, this is Professor Keen. We've been looking at William Gilbert's On Magnetism. In the previous lecture, we talked about how if you take a Torella, which is a spherical lodestone or spherical magnet, and hold a compass needle near it, that compass needle will tend to orient itself in a particular way with respect to that Torella. And the way that it behaves is very similar to the way that if you hold a compass needle near the surface of the Earth, for instance, when you're sailing on a boat and you want to look at your compass, that compass needle will orient itself with relationship to the Earth. And what Gilbert's pointing out is the relationship between a compass needle and the spherical Torella is very similar, in fact, the same as the relationship between the compass needle and the Earth itself. That is, the Torella has the same kind of nature or properties as the Earth does. And it has the same properties, these magnetic properties, because, as Gilbert argues, it has the same form as the Earth, or the same formal cause. And we spent some time in my last lecture talking about this terminology of formal cause and how its relationship or its derivative from this Aristotelian notion of four causes that Galileo was using in order to understand this. Okay? So let's continue our thinking about this, and let's talk a bit more about how when you take a rock out of the Earth, it tends to orient itself. So this is in the same section that we have been discussing. What Gilbert talks about is he says, let's suppose you think about the Earth itself. Okay? And the Earth has an inner core part. Keep in mind that there's not a lot of knowledge at this point in time. Well, in fact, there's not a lot of knowledge today even about what goes on inside the bowels of the Earth. But the idea that people had at this time is that there was a core of the Earth, and then there's a layer on top. I'm exaggerating this a bit, but a layer on top this is sort of the solid core, what's essential to the Earth, and this is the detritus, the rocks, the rubble, the kind of top layer that's less I guess it's more mobile than the interior part. And what Gilbert does in this section is he talks about, well, if we label the North Pole of the Earth over here, I know it's on its side, but I'm keeping up with what he does. The North Pole of the Earth is here, the South Pole of the Earth is here. He calls this point G, and he calls this point H. And he says, what happens, and let me just label this once again. This is the detritus, I think that's the term he used, or the topsoil, which isn't just the thin layer of soil, but it's kind of a thick layer of the stuff on top of the Earth. And this is the core, or the central part of the Earth. Okay? And he says, what happens, the central part of the Earth is magnetized. After all, that's what, it acts like a big magnet. That's why, after all, it orients compass needles. Now, if you take a chunk of this core of the Earth out, he labels this EF. So if you remove a section of the core of the Earth, and then I'll draw, so here is again the outside section, the inside section right here, and now we have this kind of hole right there. And then this is the atmosphere out here, by the way, the atmosphere. Maybe I'll label this stuff. Atmosphere, let's make that kind of a blue color out here. And the core part, let's make that brown. Okay, and the detritus, I'll just leave that white for now. This I'll make blue. The atmosphere of the Earth, the air surrounding the Earth, and water, and so on. Okay, I'll redraw it right here. So here's the atmosphere. And then the core of the Earth, but we've removed this section, this rock. And then if we were to take this section right here, I'll just color this part brown, and we were to hang it up here from a string. So take it out of the center of the Earth from a mine, let's say, and then hang it. What would happen to it? How would it orient itself? And he says if you take it out of a chunk of the Earth out, and suspend it, what would happen is it would twist around in such a way that what had been on the north side would then be on the south side, and what had been on the south side would be on the north side. Okay? And so that's what happens if you take out a chunk of the Earth that is within the Earth. Okay, again, here's G and here's H. And he argues that's because this part of the Earth is the north part of the core, this is the south part of the core, and that part that was inside shared those properties. So this end was a northish end of that rock, and this end was a southish end of the rock, because after all, the Earth has a north end and a south end. So when you take it out, what had been the north end is going to want to swing around and be attracted toward the south end of the Earth. And what had been the south end is going to swing around and want to be attracted toward the north end of the Earth. That's what happens. Okay? And he says that's going to be slightly different than if you were to take a section out of the Earth that was not in the core, but in this detritus or topsoil area. So if we were to take instead a section out up here in the rubbly area, and I think he calls this A and B. So this is a section of lodestone, or let's suppose there's a lodestone or a magnetic piece that's up here in the topsoil area, and you were to take that out, so remove a lodestone from the detritus area. Well, what's going to happen then? I'll redraw the Earth, and you suspend that. So I'll draw a hole right here. Maybe I should make this, I don't know, maybe I'll make this colored pink or something. Might as well continue to color code this. Okay, so you take this section out. It had been a pink lodestone. You take it out and you hang it up here in the atmosphere. Then what is going to happen to that pink piece right there? So if you took this and you hung it, let me draw the atmosphere once again to be consistent. What do you think would happen Well, what Gilbert argues is that it doesn't rotate. It just stays the same way that it had been. Why is that? He says it's because this lodestone was not part of the core. At some point, maybe it had been part of the core, but because of whatever activity, it ends up here. But because this is a mobile area of detritus topsoil, that lodestone is able to orient itself with respect to the core. So this lodestone, although if it was in here, it would have a north end here and a south end here, like the core itself. When it comes out, it's able to move around, and this end right here would be the north end of it, and this end would be the south end. It has already reoriented itself with respect to this core, so when you move it out even further from the detritus into the atmosphere, it doesn't need to rotate anymore. Okay? So that's an explanation that that Gilbert gives for how when you extract lodestones from a mine, how they would behave with respect to the magnetic central area of the Earth. He does another. This is a little bit speculative, I think, but what he does do is he does a demonstration of this using a Torella. The demonstration with his Torella. Remember, the Torella is his spherical lodestone. If you take a Torella, which has a north side and a south side, and you break off a piece, so you cut it, let's say, along the top like this, somehow, you break the top off. what do you think is going to happen? Well, let's draw the bottom half like this. This is the north side, this is the south side. You break the top off of it and you suspend it. What's going to happen is it is going to swing around. So if you had, let's say, labeled this end of the lodestone red, you marked it red. Of course, there's not a big N on the lodestone, but we could make a mark on it. The red end would be the north end. This swings around, so now the north end is going to be, what had been the north end of the Torella now is oriented toward the south. Why is this? Well, it's because opposite poles attract. What had been the north end now swings around, is attracted toward the south end. Okay, and you can do this. He does it, and he demonstrates this. And he says, parts with the same verticity, or polarity. He uses the term verticity, but parts with the same verticity, and probably we would say the polarity, when joined with the whole, on being separated, twist around. He says for opposite verticities or opposite poles attract. Okay, so this part right here has the same verticity as this point. It's got a north end. When you separate it, it twists around because these opposite poles attract. Let's do another example. Here's another example. If you were to take a bar magnet like this, and it has, on one end, it has a north pole and the other end is a south pole, and we could even mark these if we wanted to. Okay. By the way, how do we know this is a north pole? How do you know what the polarity of a particular bar magnet or a piece of lodestone would be? Well, as Gilbert says, you can put it on a little boat and look at the way it twists around, and whichever end is aimed toward Earth's North Pole, we'll call that the South Pole. And once again, a caveat, the conventions that Gilbert is using are going to be reversed from the modern conventions, but we'll have to come back to the point later, and it's good enough as long as we stay consistent for now. Anyhow, if you take one of these and you identify this as a North Pole, and then you take this bar magnet and you split it down the middle in this way, and you suspend one, what's going to happen is this one is going to twist around, and again I'll mark them. So the North Pole is red like this. When you do that, this one swings around so that the North Pole is attracted toward the South Pole like this. Okay, so that's another example. All right, now this raises an interesting question. If this magnet stuck together as a whole, and then when you cut it, it wants to swing around, obviously there's a tendency for the north parts to push against each other. So there must be, what is it that holds it in this orientation? There must be some kind of binding force, some competing binding force that competes against the tendency of north sections to repel each other, that keeps those parts oriented parallel to one another when they're together, but which isn't strong enough once you break them apart to still bind them together, so therefore they swing around. So really there has to, in order to understand this on a deeper level, we have to understand more about what holds magnets together, the binding force within them. But that will really have to wait until the advent of quantum theory of matter in about the 1920s or the 1930s. So I guess at this point I just want to point out that there's some difficulties here, or at least things that we don't understand yet. that Gilbert is not going to be able to address, but there will be a better strategy for addressing them once quantum theory is developed. I'm going to stop there.